Good day, everyone, and welcome to this session of mining engineering. And we'll be doing geotechnical engineering today. I'll be your tutor, Panashe, and we'll cover a single tutorial. We'll just do just about 3 questions. So we will cover geotechnical engineering 2. Okay, so our first question is asking us to illustrate, draw, and label the stress zones and or stress effects in regards to the following. Firstly, around a deep level gold mine stope. So that's the depiction we have here. This is typically what it looks like at a deep level gold mine stope. Narrow reef, that is. You have compressive stresses here on the edges, and then you have shear stresses far off coming down like that, and then you've got tensile stresses here in the center, right there, tensile. So the compressive ones are always at the edges. That's one thing you have to note. So when you do label, just make sure you label the compressives at the edges, and then the tensiles are on the top of the stopes. That's where you get most of the tensile stress, and then the shear stress on the sides. Okay, around a horizontal circular tunnel with major principal stress vertically aligned, right? So I have some depictions here of a typically circular tunnel, right, which is going through this page, through this whiteboard. So if you have a vertically aligned stress, your stress profile typically looks like that. The red dotted line, that would be your stress profile. So when you do represent it, you can represent it in that way, where the black is the periphery or the edge or the wall of your tunnel. So that was 2, right? And then here we're being told around a horizontal circular tunnel with major principal stress horizontally aligned. So it's no longer vertically but horizontally aligned. So typically you just would represent it in a tilted form to your original representation. Now you have the stress horizontally aligned, and then that's your round tunnel, and then that's your stress profile. So as you can see, the curvature here is always happening perpendicular to your stress profile. So you're going to get more stresses on the edges, right, which are focused here where the stress profile is acting. So that's basically the depiction they've asked for there in part 3 of the question. And then part 4 is saying around vertical shaft when the major principal stresses are vertically aligned, right? So when you have a vertical shaft, it would look something like this. And when you have stresses which are vertically aligned, you're saying they're going down into the shaft, right? So you won't experience any kind of stress impacts on the periphery of your tunnel if your stresses are vertically aligned. Now, if I was to depict this in a cross section, let's say that's your shaft right there. And they've said that they are vertically aligned stresses. So your vertically aligned stresses would go directly down along the periphery of your shaft. So that would look a lot like that. That would be your vertically aligned stresses. So because they're acting parallel to the wall of your shaft, you won't experience deformation or any damaging on the shaft wall. So that would be how you would depict question or part 4 of the question. Then part 5 says around a vertical shaft when the major principal stresses are horizontally aligned. Now that's a different depiction where we would have another cross-sectional view of your shaft, and then we now have an alignment which is going horizontally, right? So that means that's how the stress is acting, and that's now totally different. So when you do have such happening, this is on sectional view, as I've mentioned before. However, this was our picture on a plan view, right? And when you have horizontal stresses acting, what happens is you will have exactly this configuration as before, just viewed on a plan view. Something like that. So your shaft hole is here. So this is the top view of your shaft. Shaft hole is here, and there's that stress, right? This blue one. It's acting horizontally. So from the top, you'd view it in that way, acting horizontally. And then on a section view, you'd still see it here. So what it does is that it's causing a lot more stresses here on the edges, right? Then your hole will lose shape, and then you end up with this shape, which is what we call dog earing. So whenever you see this is a consequence of a horizontal stress which has been acting. So typically, that's what our stress is doing. So from plan view, we see the stress going there, and then we have dog earing happening on those ends. So basically, that's the first question, and that's what it's looking for really when it's asking you to draw and label. So just keep in mind all these labels we've mentioned, and add some more annotations than I have to just show that you're talking about, um, sigma 1 right here. And then, for this sectional view, you also just label it as sigma 1. Let's see if I do have a sigma sign. Yeah, so typically that's what I'd be indicating it as sigma 1. Yeah, so add some annotations so that the adjudicator or your lecturer, whoever's marking, will see what you're labeling and will know what's going on. Okay, so that's question 1. Now, question 2 says a typical 30-meter wide narrow reef stope panel in a gold mine is being blasted every day except on Sundays, and average advance per blast is 1.1 meters. Now the mining width of the stope is 1.2 meters. A line of mine pole support is installed at the beginning of the panel immediately after the first blast, before significant closure could occur. Now, after 2 weeks, the average height of these mine poles measured 1.16. Calculate the average closure rate in the stope. State all your assumptions clearly. Okay, so, this is quite visual, and we'd like to quickly just sketch what it might look like in section view, right, in a stope. So that's typically what your stope would look like, right? Now, you obviously have the center, of your strike gully, right? And you had the mining pole being installed immediately after the first blast before significant closure could occur, right? Now, these mine poles were installed, okay, I'll use brown for the sake of contrast. So we have mine poles right here. Oh, sorry about that. Let me not use a dotted line. Let's use a complete stroke right there. So these are your mine poles, right? So they've been sold at the beginning of the panel, right? Which is right here, immediately after the first blast before significant any closure had occurred. So no closure has occurred here. Now, after 2 weeks, the average height of these mine poles measures 1.16. Calculate the average closure rate in the stope. So after 2 weeks, we are expecting that they have had a certain advance. Now, advance per blast is 1.1, right? And they're being blasted every day except on Sundays. So that means 6 days of the week there's a blast, right? So that translates to blasts in 2 weeks are going to be 12. 6 the first week, 6 the other week, right? Now, what is the advance? The advance in 2 weeks then becomes the 12 multiplied by 1.1, which is the advance per blast, right? Okay, so our advance in 2 weeks is going to be 12 times 1.1 meters, which should give us 13.2. Okay, now 13.2 is what the advance of the panel has been in 2 weeks. However, we are looking at the closure rate and convergence. Now, it may seem like a trick question because we do know that this is our formula for convergence. Not necessarily closure rate, but convergence. If we can get convergence at this point, within those 2 weeks, we can get a closure rate. The problem being now, we don't have a Poisson ratio. We don't have Q. We might know how far the panel has gone, L, and X is not so clear. All we know is that this is 30 meters wide as a narrow reef, right? So the second thing we could then do is to simply look at how much convergence has happened without necessarily using the formula, because we know the initial mining width of the stope was 1.1. So initially this was 1.1. 1.2, sorry, 1.2. And then after 2 weeks, is measured at 1.16. So the closure, or rather convergence, right, at the location of the pole would be equal to your initial 1.2 meters minus 1.16 meters. That gives us 0.04 meters, right? Which is also 40 millimeters. Now, we've got 0.04. What do we know? We know that this blasting happened over 12 days, right? So we can use time, therefore we can measure the closure rate using time or using the advance. Now we know the advance was 13.2. Let's just label that quickly. Okay, here's advance right there, right? That's the advance from there to there. So that one was 13 for clarity. Okay. Now we need a rate. Therefore, we can say closure. So basic closure rate is convergence per unit time or per unit of advance, which is meters. So closure in this case would be equal to, let me just find if I can put a fraction there. Okay. Okay. Oh, not bad. Go. Okay, so our closure would be 40 millimeters divided by 12 operating days, right? Yep. That should be equal to 3.33 millimeters per day. Yeah. So that's our closure rate in okay, sorry, let me just fix that quickly so that okay, millimeters per day. So for the sake of being technically correct, you will have to just also do a quota calculation in terms of the advance. So we're at 40 millimeters still, and an advance of 13.2 meters. So we punch that in the calculator and see what we're getting. That's 3 millimeters per meter of advance. Or you can just keep it per meter, it doesn't matter. So yeah, these are solutions. That's what the question is really looking for here. We didn't have to use the formula. It was kind of a trick question. However, if you basically use simple reasoning and some calculations here, you can come to conclude that we simply have a closure of 3.33 millimeters per day, or 3 millimeters per meter of advance. So yeah, that's question 2. Then we'll move on to question 3. When the span of the same stope is 150 meters, calculate the height mine pole referred to in question 2. Okay, calculate the height of the mine pole installed 10 meters from the face. Now, in question 2, right, the span has now increased of the same slope to 150 meters. We are now being asked to calculate the height of the mine pole that has been referred to in the previous question. So we want to see how much convergence has happened. So we're going to need to use the formula for convergence. Now, you do have some given parameters. We're assuming the rock density is 2.75, 2,750 kg, sorry. You have depth below surface of 1,400 meters, a Poisson ratio, and you got a modulus of rigidity. So all of that we're going to substitute into our formula. Now, we need to know what Q is. And Q is equal to the density of the rock applied by 9.8, which is acceleration due to gravity, or G, gravitational constant, we call it so many things. And then the depth, which was 1,400. Now, that's what we're going to substitute for Q. Poisson's ratio we've already got, 0.3. And then G is modulus of rigidity, 33 gigapascals. Now, you always use basic units, so this is 33 times 10 to the power 9 when you substitute that. Right. Now, okay, where did this equal sign come from? Sorry about that. You're multiplying that with the square root of L squared. L being the half span, right? Now, here we've been told that the span of the same slope is 150, right? So the half span then becomes half of 150, which is 75. So L is equal to 75. Right? Okay. So the height of the mine pole referred to in question 2. Let's just check question 2. Right. And this mine pole was installed here. The problem is we don't have an X value. We don't have an X value. Right? So we will need to determine, not knowing how far this was from the center of the stove, right? Now, what you do have is a closure rate. Now, knowing your closure rate, you could make a good assumption that using my closure rate, the height or the convergence that has happened, right, due to advance has changed accordingly. So we've got to calculate how much convergence has happened, right? Now we can do that using our closure rate multiplied by the number of meters or the advance in meters. Hence why we've been asked to calculate the closure rate in the first place. So convergence is equal to your closure rate of 3 millimeters, right, per meter of advance multiplied by the advance. How much advance has occurred here? Well, the span of the stove is now 150. However, the half span is 75. So from where the pole initially was or still is to where the face now currently is what we're looking for, right? Now, you could obviously make an assumption that there is obviously a distance from the center to where the pole was installed. And a safe distance to work with would be maybe just about, let's say, 2 meters. 2 meters, right? So that could be an assumption. Now, if that's 2 meters, let me just illustrate that so that you guys see what I'm saying. Okay, that's brown for our poles. So there's that pole we drew last time in question 2, right? It's still there. Now there's a distance here, small distance. That's the distance there, right? And that's what I'm calling a distance of 2 meters. But then there's the longer distance from there to there, which becomes 73 meters, since it's going to be the 75 minus 2. That is the advance that has happened, right? So you could do that, or you could go back to your question, look at how much advance had happened, right? And how much convergence had happened by the time you had an advance of 13.2 meters. You had a convergence of 0.04. Now, you could go back, right, and say, okay, that convergence from last time of 0.04 happened, okay, that's too long. Let's just put it here, okay? Happened when we had traveled 13.2 meters of advance. Now, 75 minus 13.2 meters will give you the advance that it had moved since the last time we calculated, right? So 75 minus 13.2 is equal to 61.8. So we could label that right there. Okay, so we've got that and we've got that, and we know that the 61.8, right? And here we know that's 13.2. Let's put units so that we know what we're working with. Okay. Okay. So now we've figured out what's going on, we can work with the initial close rate and advance quite easily, right? Now we've got conversions of 3 millimeters per meter. We've moved 61.8 millimeters since the last time, right? So 61.8 meters. Now that gives us a convergence of 3 times 61.8 in our calculator, 185.4, 185.4, and that's millimeters. So seemingly that seems like way too much, and at that point we have to be asking why it's so big. Well, considering that you've got 61.8 meters, you would have considerably a lot more convergence happening at the same spot, right? So in meters, that's still 0.185 meters. So that's just about what the convergence would be. It is reasonable. It's not too big, although we have now given some reasons as to why it's not too big. You see? So it makes sense that it's 0.185 meters. So now the question then goes on to say, calculate the height of the mine point, so 10 meters from the face. Now this is in question 3, where the span of the same slope is 150, right? So there's another pole. Let's choose pink. So we've installed a pole 10 meters from the face. Okay, sorry, that's a bit bent. That's better. 10 meters from the face. That's 10. That's why I prefer typing. Because now I look like I was writing with my feet. But for the consideration of this pole over here, we are going to calculate how much convergence has happened at that place. Now, we do have all these parameters for the sake of the second question, right? So can start working on question 2. Okay, just leave one there. Right. We've got these parameters, right? Now, the question then becomes what x is for that pole. So it's convergence at this pole, right? Which is 10 meters from the face. Now, the distance x, let's just get rid of these. They aren't being used anymore. We're looking for x, which is from the slope center all the way here. Okay, let's draw a meter line there. X. So x is 10 meters from the face, right? Which is 75 minus 10, which means this is 65 meters. Okay? Yeah. So we now have x. X is equal to 65. So you simply substitute into your calculator and see what you're getting. Okay. Now, I'm getting 0.06. I don't know what you guys have gotten. However, it should be in that range. Meters, right? Or 60 millimeters if you want to have it in millimeters. Okay. So that's how much convergence has happened with this pole being talked about within question 1 or part 1 of question 3. Now, if dip and strike support spacing of mine poles is 1.5 meters, calculate the number of mine poles required in a panel per month. Assume that mine poles may not be more than 1.5 meters from the face. Okay? So, okay, let's then try to visualize what's going on there. Right? We have a top view of the panel, right? So typically that's what the panel is like. Now remember, we've been told the width. See, it's said to be a typical 30-meter wide narrow reef slope. Okay. Now, if you go there, we can label that to be 30 meters. And this side is 75, right? Or just about that, roughly. Okay, for the sake of illustration, let's make sure it looks accurate. Okay. All right. So the question is saying, if dip and strike support spacing of mine poles is 1.5 meters, how many poles are required in a panel each month? Right. So we've got a line of poles that we've installed at the start there. Right, so our poles are brown. So we've got a line of poles here, right? Spaced going that way, right? Then we've got these dip poles. Okay, sorry, they're not straight. Yeah, rather let's use the dotted line, which seems to be a better way to depict these. Okay. And we also have poles like that. So we've also got poles which were lined like that. And then another row in the panel, right? Now, what we do know is that there is a required distance here. Okay. Where the poles are not supposed to exceed 1.5 meters away. That's the distance. And then here we also have another row at the face, right? So sometimes you leave a row, and then when you're blasting, you might remove it. Sometimes it's actually some props of any other kind, which aren't necessary poles. So there may be hydraulic props, but in most cases, they would be poles. So the question has described as poles, or calculating the number of poles. Okay. So what is our monthly advance? Because in that case, we can know how much poles are required per month once we know how much we've advanced within the month, right? Agreed? Okay. So now we are calculating monthly advance. Okay. Now let me just move then these things are interfering so that we just have clarity there. Okay, let's just group this and put it back where it belongs in the panel. Okay. No, we left something out. Okay. There. Yeah, so the black line was just there to significant to be the sign for the 1.5 meter distance. Yeah, signifies the 1.5 meter distance from the face and from the edge of the panel. So we are calculating monthly advance. Remember, we have got 6 days of blasting, right, within the week, and we are operating for 4 weeks within the month. So that gives us 24 blasts multiplied by the advance per blast, which is 1.1 meters, right? And what total does that give us? It should give us 26.4 meters as a monthly advance. Now we do know that L is just about 75 meters. However, for the sake of accuracy, we can reduce it, because the distance from the center here to the first pole counts as, a distance that is not supported until we get to the first pole, and then the poles come after that. So that is just about 2 meters. So you can write that assumption down to say L is 73, assuming 2-meter distance without poles. Okay. The width was 30, right? So let's just label that W 30 meters, right? And then the stoping height, or usually called SM, right, is equal to 1.2. Then our spacing between poles is equal to 1.5. Okay, so if we go back to the question, it wants the number of mine poles required in a panel each month. Now, the panel is moving a certain advance every month, and within that month we've used a certain number of poles. So if we were to depict that, we could simply redraw that triangle, which is going to be slightly smaller now, right? There we go, right? And in this case, the panel width is still 30 meters, agreed? However, the advance is 26 meters. Okay? And then you've got a spacing of 1.5, right? Now, this is just going to be some simple mathematics where we want to see how many poles are along the dip and how many poles are along the strike, right? So poles, poles on dip is going to be equal to 26 meters divided by 1.5 spacing, correct? So let's punch that in our calculator. 26 divided by 1.5, which gives us 17.3. So that's just about 17. You can't have 0.3 of a pole, so for accuracy reasons, let's say 18 poles. Okay? And then here, poles on strike. Right? equal to 30 meters divided by 1.5. Okay, which gives us 20 poles. Okay, so here we can assume that most of our poles, right, are going to be installed along strike and along dip. However, what happens, okay, what happens where we have finished mining, we will probably have smaller installations, right, of mat packs or any other kind of material that supports. So at a very, very deep level of mining, you wouldn't be using poles the way we're using it. So here, consider that we're mining at 1,400 meters, right? Each time we're advancing in the panel, we will have to leave some more permanent support. So you're going to have your primary support systems right here and there, which are these poles. So we can then say that we use just about 18 plus 20 poles, which gives us 38 poles within a month. Total of 38 poles. Per month. Okay? So yeah, I think that's our solution to there, so that you see clearly. That's our solution for part 2. Now, we have to calculate the average convergence when the span is 90% of the critical span. Considering we have formulas, that's going to be an easy task. So there we go. We can then begin calculating what we need there. Firstly, we must see what parameters we have to work with, right? We need the stopping height, your SM. Okay. That's 12. Yes. Okay. Which is 1.2, right? From the previous question, we know that our sloping height is 1.2, right? We do have G. G is equal to 33. As you can see from what we were given previously there, that's the same information we are using now. This is times 10 to the power of 9. right there. There. Okay. Okay. 10 to the power 9. We need V, which is the Poisson ratio, which was 0.3, if I'm not mistaken. Yes, 0.3. Q, which is rho GH, density times a density of 2750 times 9.81 times 1400 depth. Okay, so we substitute that into our formula, then we find a solution, and you should be getting 749, 740, 8.9, but let's use 9. Let's round it off. 749. Okay, meters, that is. So that's the critical health span. That's where convergence has happened at the center of the stope completely. Right. However, the question here then has said when the span is 90% of the critical span. So the actual span would be 90% of the critical span. Okay. So our calculation continues. So the span, right? Oh, let's write span so that we don't have confusion. Span is equal to 90% of the critical span, which was 749 meters. So 0.9 times 749 in our calculator gives us 674.1 meters. Okay. Now, knowing our empirical rules, the formula we're going to use, right, is this one in order to calculate our convergence. Why? Because our span, L, is actually less than our critical span. Right? LC. C. Yeah. It's not small enough, but yeah. Anyway. Okay. Maybe I didn't highlight, that's why. Yeah. So L is less than LC, right? Hence we use this formula. Okay. So we substitute everything in there and see what we're getting. We've already got, we know pi is a constant, Poisson is 0.3, L is 674. Okay. Don't get it mistaken. That's L. Q is already there. G is already there. So you take all those figures and substitute them, and see what you get. Okay. Okay. You should be getting an average of 0.85 meters. Yeah, because that's quite a long span. That's a very, very long span. And considering that you're approaching the critical half span, it should be close to 1.2, right? At which you know that when you've reached the critical half span, total convergence will occur. So, yeah, that's part 3 of question 3. And now we will take a break. So, we'll be back soon to continue with question 3.